each mean uh, when I go towards the end of the talk. So feel free to interrupt me at any time, unmute your microphone and ask any question, or you can also put it in the chat, because it's possible that I could run into jargon of notations without realizing that I'm confusing you all. So don't be shy to ask any question, and I will be more than happy to answer all of that. And I should also mention that the purpose of this talk is not to teach you the details of algebraic number theory or Iwasawa theory, because that could take years. The purpose is to make you all interested in algebraic number theory, at least to tell you what algebraic number theory is and what Iwasawa theory is. I just want to expose yourself to this stuff. And during the talk, I'll have to use some notation because I have to use them. But don't get lost in the notation. Try to get the big picture or the general idea of what I'm talking about. Okay. But if you have a question about the notation, I'm happy to answer them. All right. Okay. So I'll start from the word algebra in the topic. Okay. So let me start there. Can you all see my screen? Let me take the full screen. Can you see my screen? I hope you. So yeah, if you cannot see it, please let me know. Okay, let me continue. All right. Okay. So okay, the first question is, what is algebra? I'm talking about algebraic number theory. First, we need to understand what algebra is, right? So algebra is, by definition, the study of unknowns. So when we were school kids, we learned that, okay, we use symbols to learn algebra. We use symbols to denote real numbers, so maybe in high school, complex numbers, but we don't know what their values are. But we already knew that they're complex numbers or real numbers, right? So they were unknowns, but not so much, because we didn't know their values, but we knew they were complex numbers or real numbers. For an example, we use symbols A and B to denote the real numbers, such that their product is 6, and their sum is 5. So there are real numbers out there where that happens. And maybe Z is a complex number where e to the power Z is -1. So we use symbols to denote real numbers and complex numbers which we don't know. That we called algebra back then. But in abstract algebra, we take this algebraization to another level. Now we don't even know what objects we are talking about. Earlier we knew we were talking about at least real numbers or complex numbers. Now we are algebraizing the objects, or like the mathematical structures themselves. And then in that way, we can study those mathematical structures all at once using their common properties. All right. So in that way, we don't have to study each of those mathematical structures separately. To a certain extent, we can look at their common properties and make an object out of those common properties and study that common property. In that way, we do things much more efficiently. I think that's a good way of division in the labor in the mathematical community. I think it proven to work. All right, so let me give some examples of what I'm talking about. So the first example is a group, the concept of group. So yeah, I'm going to introduce some notation, but I'll give some concrete examples at the end too. Okay. All right. So a group is a set with a binary operation. G is the set, and star is a binary operation. It could be any binary operation, which we don't know, but it should satisfy some conditions. For any element, any 3 elements A, B, C in the set G, A star times B star C should be equal to A star B star C, which means which we call the associativity, which simply means that it shouldn't matter which order we choose to apply the operation. We could apply the operation first to B and C and then do A, or we can do it to A and B and then do C. So it shouldn't matter. The second condition is there's an element which acts neutrally under this binary operation, which means if there's any other element A star E should be same as A, and E star A should also be same as A, which we call the identity element. So it acts neutrally, it doesn't do anything. And we should also need an inverse element for any element A. So if you have any element A, there should be an inverse element, which means an element B such that A star B and B star A is 1. I think it's a typo, but not at the same time. By 1, I mean the identity element E. Okay. So, and we denote it by A inverse. So I should say these elements A, B, and all the elements I'm talking about, they are not necessarily real numbers. They could be anything. They could be real numbers. They could be matrices. They could be element in a finite field. They could be a function. They could be a polynomial. Anything. So that's what I'm talking about when I said we algebras in the objects themselves. They can be anything. All right. And in addition, if A star B and B star A are the same, we call the group G abelian. It's not necessary. So order of multiplication shouldn't matter. Okay. So let me give some concrete examples. Okay. So if you look at the set of integers under usual addition, so that satisfy all these 4 properties actually. So is the rational numbers under multiplication, right? So those are abelian groups with abelian groups, right? And the third example is you might have seen this example maybe in computer science, I don't know. This is integers modulo 5, which means in this set 6 is same as 1, 7 is same as 2. We are looking at the remainder when the integers are divided by 5, and we add it in the usual way, but we take the remainder all the time. So this is the group Z over 5Z under modulo 5 addition. So first 2 groups are infinite groups, right? There are infinitely many integers, there are infinitely many rational numbers. The third group is a finite groups. It's a finite group because it has only 5 elements in there. So there are infinite groups, there are finite groups, and all these 3 examples are abelian, which means it doesn't matter you add 2, like if you have 2, for an example, in the first example, in the first group, if we have 2 integers A and B, A plus B and B plus A are same, right? So it's abelian. Same in the other 2 examples too. But there are groups out there where that's not the case. This is an example you might already know. I'm looking at invertible n by n matrices with real entries, which has the notation to be GLNR. So in that, this is still a group. So all the first 3 axioms are satisfied, but we all know that matrix multiplication is not commutative, right? If we have 2 matrices A and B, AB is not necessarily same as BA, right? So it is a group, but it's not abelian. Okay. So as you can see, these are seemingly unrelated mathematical objects, right? Matrices doesn't have much to do with Z over 5C, but all of them are groups. So we can study groups, and that study will have implications in all of these mathematical structures. That's why this is a very efficient way of doing things. All right, any questions from this slide? Because I'm gonna discuss about groups over and over again. Yeah. So I would give you a non-example too. This is a mathematical structure, like a set with a binary operation, but these are not groups. For instance, real numbers with multiplication. It's not a group. Why? 0 doesn't have an inverse element, right? 0 cannot be inverted under multiplication. The second non-group is positive integers under addition. It's not a group. Why? If you take the integer 1, it doesn't have a additive inverse. You would say it's -1, but -1 is not a positive integer. Additive inverse should lie inside the set we are considering, okay, for that to be a group. All right. So yeah, we have a bunch of examples and non-examples. So now we have some idea what groups looks like. but we still don't know what these are good for, right? What does this characterize? What is it encoding? Actually, it is encoding a really fundamental phenomena, which we have noticed from our childhood. What this characterizes is the concept of symmetries itself. So, uh, so from our experience, when we say symmetries, we automatically think about geometric objects, right? That's what we are used to visualize. That's a good place to start. So yeah, symmetries are present in a lot of geometric structures, and groups are the way to study them. Well, I would say it's not only the way or the tool to study symmetry. I would say it's equivalent to the concept of symmetry itself, but I'll talk about it later. Okay, let me give some examples. If you take a regular n gun, what's an n gun? Regular n gun, it's just a polygon with n uh, sides and n vertices, which equal sides, equal length sides, and equal angles. So there are symmetries in that, right? There are rotational symmetries. You can like rotate the polygon n times, right? So that rotational symmetry is characterized by the group Z over NZ. So under addition, integers modulo n. That means we are considering the remainder when things are divided by n. Because if you go a full circle, it's same as doing nothing, right? That's why we are only considering the remainder. So in regular n-guns, rotations are not the only type of symmetries, right? There are also reflections. So we can put together all of these possible symmetries, and that will give us what we call the dihedral group. Okay, so this group is very well understood. We know what all the elements are. We know how to multiply all the elements, and it's a very well understood group. It's a finite group. It has two n elements, n rotations and n reflections. All right. Okay. The next example is one of my favorite examples, the Rubik cube. Rubik cube is a object which has a lot of symmetries, right? Because what you do when you like uh, put actions on, like do rotations on Rubik cube is you are you are you don't break the Rubik cube, which means you are not breaking the structure of that object, but still it encodes a lot of symmetries. As a result, the group attached to the symmetries of the Rubik cubes is a non-abelian group, and it has order of this big number. It's called the Rubik's cube group. So okay, I said this is a non-abelian group, right? It's in Rubik cube language. It's same as saying if you rotate the up face once and the left face once, that's not the same as rotating the left face once and the up face once. So those two are not the same thing. I mean, you can do it and see. So that's why it's not an abelian group. Doing A first and B second is not the same as doing B first and A second. We know though that this group is generated by 6 operations, right? So there are 6 phases. Rotating each phase is rotating each of the phases are the operations. It's generated by these operations, but these are not all the elements in the group. Okay, there are like this number of like this big number of elements out there, but these are the generators, meaning any element in the group can be written as a multiplication of these 6 operations. So okay, yeah, before talking about the methane molecule, let me also mention a theorem in group theory, and I'll reinterpret it in terms of the Rubik cube. Okay, so there's a theorem in group theory. It's a not very hard theorem to prove. If you have a finite group, if you take any element in the group, if you raise it to the power of the size of the group, you should get the identity element. So you take any finite group, you take a element G, you take G to the power size of the group, then it is the identity element. So what does that say in Rubik cube language? So what that means is you take the Rubik cube, you shuffle it around, but you remember how you shuffle it around. Okay, you do certain shuffling. So what the theorem says is that if you perform the same shuffling operation this number of times, this order number of times, this 43, 25, blah, 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 that number of times, you will eventually come back to the beginning, come back to the come back to where you started from. You will have solved the Rubik cube. Yeah, that's what it means. But what it means, what that's the meaning of that theorem in the Rubik cube language. Because as I said, taking g to the power that the order of the group is same as the identity element. Identity element is same as doing nothing to the Rubik cube. So we would uh, end up where you started from. Uh, but you don't have to do it that many times. Usually it's you don't have to do that many times. You can do it in a lower amount of steps. And also it's famous, I think, that no matter how much you shuffle it, you can always solve the Rubik cube by 20 moves, right? I think that's famous. In the group theory language, what it means is that if you take any element in this group G, uh, it can be written in a string of 20 characters using these F's and B's. You are allowed to square these elements, but yeah, that's what it means in the group theory language. All right. Okay, now let me talk about the methane molecule. It's a simple enough molecule, right? And certainly it has symmetries, and they are characterized by this alternating group of order 12, A4. So I won't try to give the definition of that. I'll roughly mention that group correspond to swapping swapping hydrogen molecules even amount of times. If it's not clear, don't worry much about it. It's just that A4 is well understood and that characterize the symmetries of the CH4 molecule. And chemists would find this very interesting, and they use these kind of things all the time. And as I said, uh, the study of symmetry is equivalent to the study of groups. Groups are not just a tool we use to study symmetry. It is the symmetry itself. And we know in the universe there are a lot of symmetry, right? And physicists study symmetries in our universe all the time, and it's not surprising that group theory shows up naturally in quantum mechanics and in other theoretical other fields of theoretical physics. I don't know what these groups are, to be honest, Lorentz group, Poincare group, but I just put it in this slide. So if you're interested, you can look this up. All right. Any questions? Okay. Let me move on. So yeah, again, when we talk about groups, the first thing that should come to your mind is symmetry. We are studying symmetry, like what we are studying exactly symmetry, nothing more, nothing less. But apparently, some groups can be decomposed into smaller groups. I wouldn't say much what I mean by decomposed. There's a formal definition of what I mean, but let's just pretend that we know what decomposing means. Okay, so which means like big symmetries can be broken down to smaller symmetries, right? uh, and we can look at atoms of symmetries, which I call simple groups. Simple groups are groups that cannot be decomposed to smaller groups. So these are in fact the atoms of symmetries. And so this has been fascinated mathematicians for a long time, actually since they started defining the group itself. In So all the finite simple groups were classified very recently in 2012. This started in 1833, like soon after Galois. Everest Galois defined what a group is, and the proof is estimated to be 5,000 pages long. And it's done by many, like hundreds of mathematicians over the course of like 200 years. Yeah, around 200 years. Yeah, several parts of the classification theorem is proved by several mathematicians, and yeah, a lot of things happened in this area. But finally, in 2012, we we won, and we now have a complete, I would say, periodic table for symmetries, right? I'll mention the theorem. um, I'll describe it as much as possible, but yeah, let me see. So this is the theorem. This is the classification of finite simple groups. So every finite simple group is isomorphic to, which means it's same as one of the following groups. So there are four families of groups. First one is cyclic group of prime order. That means the group of rotational symmetries of a polygon who has prime number of vertices. Okay, it's a cyclic group. Yeah, you rotate it prime number of times. So an is the alternating group of order n. So I explained A4, so it's very similar to that. And there are groups of Lie type that I'm not going to explain, but that's reasonably well understood. I think they are very. I mean, all the first three families are infinite families. There are infinitely many cyclic groups of prime order, simply because there are infinitely many primes out there, and for each n, there's an alternating group. And there are several families of Lie groups, and they are infinite families. So there are, unlike the atoms in chemistry, atoms in symmetry has infinitely many of them. So it's an infinite periodic table. And also there are these 27 like groups which are like isolated out there. These are not infinite families. These are like randomly scattered, I mean, not randomly, but random 27 groups which are out there. I mean, mathematicians are struggling to understand what these are and why they are out there. It puzzles me a lot, actually. And so these are called sporadic groups. And the largest of these sporadic groups is called the monster group, and it contains most of the other, I think 20 of the other sporadic groups. And yeah, people are still struggling to understand what monster is actually. So as I said earlier, all the groups are describing some sort of symmetry of some object, right? So it turns out that this monster group has the order of 8, approximately 8 times 10 to the power 53, and it's describing symmetries of an object living in uh, 196,883 dimensional complex vector space. So yeah, it is describing some element or some object out there living in this huge vector space. But yeah, it's not very well understood, I would say. Um, yeah. So okay, I should also apologize if there's anyone who is an expert of representation theory in the audience, because I'm using this vague language like an object living in this vector space. What I really mean is there's a faithful representation from the monster to a complex space of complex vector space of this dimension, and it's a faithful representation, and this is the minimal dimension for such a faithful representation. Okay, so that's what I mean, but in more user-friendly terms, I'm just saying that it's living in this in this dimensional space. And it also describes symmetries of some other objects as well, such as what you call the monster vertex algebra. And uh, some of the objects that shows up in this area coming from theoretical physics, which kind of doesn't surprise me, actually, because I mean, as I said earlier, when I talk about the concept of groups, like intrinsically, what I'm talking about is symmetry, right? There's no way to avoid symmetries, right? I mean, if you are doing physics, you are understanding the universe, and symmetries are inevitable, right? So I would expect the monster to show up in theoretical physics in some form or another. So here theoretical physics is used to understand the monster. It's not the other way around, but there are speculations that probably in the future monster will show up in theoretical physics. And I should also say that I mean, this puzzles me a lot. As I said earlier, even when you utter the word symmetry in your mind, like the groups pops into existence, so does the monster, right? So why is it, why does it have to be of this order? Why is this number so special? It cannot be this is part of the address of our universe, right? This should be common to all the possible universes, right? It's symmetry. I mean, I can't think of any universe where symmetry, concept of symmetry doesn't exist. But yeah, it's really, really strange, and a lot of mathematicians are puzzled by this. So yeah, I used to think that one day in the future, if aliens visit Earth, one of the first things I would like to do is compare their mathematics with our mathematics. But it's possible that their notations are different, and they might have studied some different parts of mathematics than us, right? But this is something we should compare. I would show them this number and ask them whether they recognize this number, right? I mean, if they come up, if they say, oh yeah, this is the monster group, the biggest sporadic simple group out there, then I'll be very satisfied. If they don't recognize this number, I wouldn't consider them as so advanced. All right. Yeah, that's the end of my passionate rant about the classification of simple finite groups. I have to say the groups will appear in the later part of my talk over and over again, but uh, the classification of simple groups will not appear from this point onwards. So I just really wanted an outlet to talk about these things. So that's why I talk about it. I think it's really important, and I hope you find it very interesting. Okay, let me move on to another uh, algebraic structure, which is field. A field is a set endowed with two binary operations as opposed to groups. So in groups, you had only one binary operation, right? So in fields, there are two binary operations, which we call addition and multiplication, but it doesn't have to be the addition and multiplication, you know. Okay, so we just call it the addition and multiplication, right? It should satisfy a bunch of properties which we desire. It should the addition should be associative, just like this. It shouldn't matter in which order we add or we multiply, and it should be commutative. If you do it in reverse order, it shouldn't matter either for addition and multiplication. And there should be neutral elements for both operations. For addition, there should be neutral operations which we call zero, and for multiplication, there should be an identity neutral element which we called one. Again, this 0 and 1 does not necessarily mean the real number 0 and the real number 1. This can be anything. This is 0 can be a zero matrix. This 1 can be the identity matrix. We don't know. Okay, so yeah, it can be anything. And also yeah, there should, for any element A, there should be an additive inverse. So when the addition operation is done, they should vanish. There should be an multiplicative inverse as long as the element is not 0. Okay, and also we should have this compatibility between these two operations, so they should behave nicely, which means they should satisfy this distributive law. I'm sure when I say this definition clearly, a couple of examples must have popped into your head, right? Real numbers is a field, clearly, right? Complex numbers is a field. So yeah, and rational numbers is a field under usual addition and multiplication. And look at the second, this example, the set of rational functions of one variable. So what's a rational function? A rational function is a polynomial divided by a polynomial, right? So those are called rational functions. If you take all the rational functions out there, which are real number coefficients, that's also a field, right? So you can take the reciprocal, right, of rational function. That means you can take an inverse, you can add rational functions, multiply them, and so on and so forth. It is a field. And look at this example in the bottom of the page. This is an example I'm going to use later on. Okay, so this is Q adjoint root 2. So what are the elements in this field? It's those are the elements of the type A plus B root 2, where A and B are rational numbers. Okay, remember, not real numbers, rational numbers. So these This field is inside the field of real numbers, but it's bigger than the rational numbers, not smaller than the real numbers, right? Yeah, so this is also a field. All right, so now let's talk about field extensions. Sometimes fields can contains in some other fields, right? So in such situations, we call it a field extension. If we have two fields like this, if f is contained in h, we call it a field extension. When this extension is nice in a certain sense, if you already know Galois theory, what I'm talking about is an extension being Galois. If you don't know what it is, don't worry about it. It's some niceness condition. In that case, we can investigate the symmetries of the top field while the bottom field is fixed. So most of the examples I mentioned earlier when I was talking about groups were geometric objects, right? But geometry is not the only place where symmetries are present. Symmetries can be there in algebraic structures too, right? So what do I mean by symmetries in top field? So you have top field, you have bottom field. So what are symmetries? Symmetries means like shuffling around of the objects uh, without breaking the object itself, right? In Rubik cube, we shuffled around the Rubik cube without breaking the Rubik cube. Here, what are the symmetric of the top field? That means you want to shuffle around the elements of the field without breaking its field structure. Okay, when you shuffle around, the it should still be a field. And we have another condition on that. We also want to keep the bottom field fixed without changing the bottom field. So that's a certain amount of that's a set of symmetries out there, right? What are the symmetries? Shuffling around of the top field without breaking the field structure while keeping the bottom field fixed. So that gives us a group which we call the Galois group of this field extension. It denoted by gal h over f. Okay, I'll give you an example. So if you look at this extension, so we have q, the rational numbers, and we have q root 2, elements of the type a plus root 2b. So it's a field extension and it's nice. Take my word for it. And you look at the Galois group of that. And it turns out that the Galois group of this field extension is z over 2z. So it's the only group of two elements actually. So yeah, so I was talking about symmetries, right? Okay, what do you mean this group is, sorry, z over 2z? What are the symmetries I'm talking about here? So okay, I can explain it very concretely. So in the group 0 to Z, there are two elements, 0 and 1. Okay, those are the only two elements there. 0 doesn't do anything, right? It's a trivial symmetry. You are not doing anything. You are not shuffling the Rubik cube, right? You're not doing anything. What one does is you shuffle root 2, which means you shuffle root 2 into minus root 2. So if you have the element a plus root 2b, it's this one is changing it to a minus root 2b. So when you have field, or when you have field element a plus root 2b, this non-trivial group element in this Galois group is changing it to its conjugate. So that's what this group is doing. So it's shuffling around without breaking the group field structure and keeping the q fixed. Why? So if you look at the element of q, if you write it as a plus root 2b, b is 0, right? It's just a, right? So what's the conjugation of a? A itself, right? So as we expected, this Galois group doesn't do anything to the bottom field. Okay. All right. Are there any questions? Please feel free to ask any questions. Okay, I don't want to lose any of you in the middle. Yeah, and also I'm repeating this. Try to get the general idea of what's happening. Okay, don't get lost in the notation. Notation can be confusing, and I mean it's gonna get worse. The notation is gonna get worse. So let's look at the big picture. All right. So okay. So far I talk about the very first word of the topic of the talk, right? Algebra. So now finally we are talking about number theory, right? So in number theory we study integers. So algebraic number theory means using the techniques of algebra to study number theory problems. So what are these problems we are talking about? I'll list some of them. Are there infinitely many primes? This we know. There are the answer is yes. This has been proved by Euclid I think 2300 years ago. And slightly different question is, are there infinitely many twin primes? So twin primes are primes whose gap is 2, like 11 and 13 are pair of twin primes, 19 and 17 are twin primes. So the question is very close to the first question, but still we have no idea what the answer is. It's an unsolved problem in mathematics. We don't know. Yeah. So a slight change of a question can uh, change the difficulty of the question by a very large margin. Are there infinitely many primes of the form 2023 n plus 18? So the answer to this is yes. So there's nothing special about these numbers 2023 and 18. I just put them because it's today's date and the year. The only condition is these two numbers 2023 and 18 should not have any common factors. If they don't have any common factors, it's guaranteed that there are infinitely many primes of this type. And this is not easy to prove. The proofs really need 20th century mathematics. Actually, this was proved I think very recently. I don't remember the exact year. I think 2007, but I'm not sure. This was proved using analytic number theory. So we have to use analysis and a lot of other things too. Yeah, but the question is simple enough, right? Anybody can understand the question, but yeah, that's very common in number theory. Yeah, you can raise very simple questions, but the proofs are either hard or impossible sometimes. Another question is, are there infinitely many primes of the form n squared plus 1? Well, there are some. 5 is one of them, right? 2 squared plus 1 is 5. And what else? 6 squared 1 plus 1 is 37. That's one of them. But the question is whether there are infinitely many of them out there. We don't know. Still, we don't know the answer to this question. And what are the integral solutions of this equation? So when n equals 1, it is easy. And n equals 2, it is not trivial, but can be solved. When n is bigger than or equal to 3, it's very hard, and it's called the Fermat's last theorem. It's a very famous theorem, and it also requires 20th century mathematics. You need algebra, you need algebraic number theory, you need analytic number theory, you need elliptic curves, automorphic forms, and things coming from all over the place. You need it. So certainly I cannot give the proof here because the margins of this slide is not enough to contain the proof. So yeah. All right. Another question is, are there any odd integers whose sum of all proper factors is equal to itself? So this is also an unsolved question because we are looking for odd integers. If it was even integers in the question, it's known and they are well known. For instance, if you take the number 6, what are its proper factors? 1, 2, and 3, right? And their sum is 6, right? So those numbers are called perfect numbers, and we know what we know there are infinitely. We know what a perfect number looks like. We have a reasonably good understanding about that, but we have no idea whether there are odd perfect numbers at all. We have never found one. I mean, now we have these big computers, right? But still, we have now found one, and it's conjectured and it's guessed that there are no such odd number. But we don't have a proof. We have no idea how to prove it. And another question is, are there arbitrarily long arithmetic sequences whose all terms are prime? So for an example, is there a arithmetic sequence, which means sequence which every neighboring term has the same gap, right? What you call samantara shreni, right? So are there big arbitrarily long such sequences whose each term is a prime number? So for instance, is there a arithmetic sequence of length 1000 where each of those 1000 terms are primes? The answers to this is yes, and the proof is very hard. This is proved by Ben Green and Terence Tao. And the proof uses the ideas from dynamical systems, which is initially used to uh, understand the climate and other complicated systems. But apparently there are techniques that coming from the study of dynamical systems, which can be used to study number theory questions, which is really surprising and cool. And another question is, in how many ways one can write down an integer n as sum of four squares? This is also done. I think I would say this needs 19th century mathematics. We can use the modular forms. You can answer these questions. Yeah. All right. So those are kind of questions we encounter. Uh, yeah, but to answer these questions, we'll have to ask much deeper questions. So these questions are very easy to understand, right? I mean, even though they are very hard to prove, they are easy to understand what these questions are. But to answer these questions, we'll have to ask ourselves more complicated questions. Those are not very easy to state, and I'm going to be addressing some of them. Okay. All right. So okay, so we are studying integers, but why do we care about these things? That's a good question you might already have in mind right now. So let me break this question into two pieces. Why do mathematicians care about these type of questions? uh, the vast majority, almost all the mathematicians I know, for almost all the mathematicians I know, the reason is mathematical curiosity. They really want to know what's going on with integers. We believe that integers are fundamental uh, to any interesting formal logical system, I would say. So therefore, problems about integers keeps us awake all the time. So really, we really want to understand them. Uh, and if you are a mathematician and still not a number theorist, still that should interest you, because number theory is intimately connected to almost all branches of mathematics. I cannot name a branch of mathematics where number theory is not related to. Even in my own research, which is very specialized, and I'm doing like one thing, I'm using techniques coming from analysis, geometry, topology, group theory, everything from all over the place. So yeah, it is very well connected. And we use results from outside number theory, and also we pay some of our debts back to other areas. Number theory is sometimes used to solve problems in topology. So we uh, the information get transferred in both directions. So I think it's well connected. So even non-number theorists would want to understand these things. Okay, but I cannot expect everybody to share the passion I have towards integers. So which is totally fine. And if you are one of them, I hope not, but if you are one of them, why should they care? Why should non-mathematicians care about these things? I think still there are very good reasons to do that. Number theory is still connected to disciplines outside mathematics, and that makes it more applicable. If you are a theoretical physicist, if you don't have the mathematical curiosity, if you still have the scientific curiosity, you should care about integers, because, as I said, just like the monster group, the integers, the uh, number theory and integers and related objects pops up naturally in theoretical physics. We in mathematics sometimes we use ideas coming from quantum field theory and nuclear physics to solve problems in number theory. So it's kind of surprising and not surprising at the same time. I think it's really cool, and it's to be expected more and more in the future. So if you are a theoretical physicist, this should excite you. And if you are not, if you are a very practical person, still uh, this should be interesting to you, because this has a lot of applications in computer science. I don't know much about that because I'm not an applied mathematician, but I think you all maybe you all are aware of these things more than I do. So I think in signal processing, cryptography, all of those things, number theory is used a lot. So I think it's very applicable. So I will leave it at that. Yeah. All right. So okay, now let's talk about number theory. So again, this is the study of integers. At least that's how it's originated. But that's how it originated, because all the fundamental question I asked a couple of slides ago are about integers. That's how it originated. But inevitably, we'll have to ask much deeper questions. In the past and even now, uh, solving equations played a central part in number theory. Examples being Fermat's last theorem, right? Let's do an example, okay? The first example in today's class. You have this equation, okay? X squared minus y squared equals 21. If you want to solve it in real numbers, there are infinitely many solutions, right? For any real number y, there will be a real number x. So it's not very interesting. But if you restrict ourselves to integers, we can ask, okay, what are all the integers out there which satisfy this equation? So since we are in integers, factorizations would come in handy, right? You can factorize the left-hand side and right-hand side, okay? And you look at one of the factors in the left-hand side, x minus y, it must be a factor of the right-hand side, right? So what are all the possibilities? Plus or minus 1, plus or minus 3, plus or minus 7, and plus or minus 21. You can look at all of these possibilities and do some, then solve for x and y, and that will give you this set of solutions. And we know that since we've run through all the possibilities, we know that those are the complete set of solutions for this equation. This was possible because we could factorize expressions in the ring of integers. But there's another thing we might overlook. We are assuming that the factorization in integers is unique, right? So we are assuming that 3 times 7 is the only way you can factorize 21. I mean, you might say, of course it is the only way, right? I mean, because it's the prime factorization. Yeah, it is the case. I will revisit, hold that thought. I will revisit that, what I said in a couple of slides, okay? For now, yes, we know that the factorization is unique and we are using it. It's totally fine. Okay. All right. Okay, let me change the equation a little bit. So here it was x squared minus y squared equals 21. Now I'm looking at this equation, x squared minus 2y squared equals 21. So the slight change of things, slight change of coefficients makes things really different. So earlier, what did we do? We factorized, right? And we played the unique factorization game. So we wish we could factorize, right? But we can't, right? We wish we can factorize it like this, right? X minus root 2y, x plus root 2y. Well, we can factorize this, but this doesn't help. Why? I mean, so okay, can we apply the factorization of integers? No, because right hand side we have an integer. The left hand side we have broken it into irrational numbers, right? So the factorization doesn't help. I mean, this is not useful. So it looks like staying in the integers is not very helpful to solve this equation, and it's almost impossible to solve this equation staying in integers. Same is true for Fermat's last theorem, actually. So again, you can't factorize this right away, but if you step away from integers, you have a factorization. So here zeta n is a primitive nth root of unities. So zeta n is exactly this, e to the power 2 pi I over n. And you can factorize this xn plus yn in this way. So now you have a factorization in the left hand side. Right hand side is already factorized to a certain extent. But I mean, you can't say you cannot use the unique factorization of integers because left hand side is not factorized as integers. So we got to do something about that. As I said, we have to step outside rational numbers or integers. So that's what we are going to do now. So this little by little algebra is coming into the picture, right? A number field. So now fields have to come to the picture. So Q is a field, but not a good enough field to deal with questions like this. So a number field is an algebraic field extension of Q. So what do I mean by that? Uh, so it's a field extension, which is some field containing the rational numbers. What do I mean by finite algebraic? What I mean by that is every element in H should be a solution to a polynomial equation with Q. So it can have values like root 2, root 3, I, things like that. But H cannot have values like pi, because pi is not a solution to an algebraic equation with uh, rational coefficients. Okay, I'll give an example. No, I didn't give an example. An example would be Q adjoint root 2, the elements of the type A plus root 2b I mentioned earlier. That would be a number field. Okay, because all the elements in that field are roots of polynomials with rational coefficients. All right. So in rationals in Q, we had integers, right? Inside Q, we have this discrete set Z, right? It's equally spaced, like a nice little discrete set inside these rational numbers. In number fields also, we have a concept like this, which we call the ring of integers for a number field K. If you have a number field K, we define the ring of integers of that number field to be all the elements in that field, uh, which are roots of a monic polynomial with integer coefficients. So since A is already in the field K, so since K is an algebraic field, it should be a solution of polynomial equation with rational coefficients. But now we are demanding that the roots are, so the coefficients of this polynomial is integer coefficients as opposed to being rational. So yeah, this is some notation. Don't worry if you don't, if this notation and definitions are not sinking into your mind right now very well. Think of this as the set of integers. So you have rationals, integers, just like that. We have number fields, ring of integers. Okay. So yeah, so it's like you can think of it as like the rationals are there, like, and integers are like the skeleton of the rationals, right? So it's like that. The number fields is there. It's inside the number field. You have the skeleton of ring of integers, which behaves like this ring of integers. Some example. So ring of integers is Q is Z, as I mentioned. The ring of integers of this set, elements of the type A plus minus root 5b, where A and B are rationals, is Z adjoint minus root 5b, where A plus minus root 5b, where A and B are integers. So this already has the integral flavor, right? It's like a discrete object. So yeah. And this ring of integers of general number fields do satisfy some properties of some properties of integers itself. So in our minds, you should always think about the string of the integer Z when you think about the ring of integers of a general number field. And this is a theorem that it's in fact a ring. So this is some notation I didn't introduce, but if there's a person who is familiar with ring theory, you know what I mean. For those who aren't familiar with that, I would say this simply means that if you add and multiply two integral elements, you again get back an integral elements. Okay, so that means if in the ring of integers you can add and multiply. That's pretty much what I mean by this. Okay. All right. So this is the problem here. So okay, it is very similar to the ring of integers Z, but the rational integer Z, but it does not necessarily have a unique factorization by reducible elements. So remember when I saw the equation x squared minus y squared equals 21, I factorized and I used the fact that any integer can be uniquely factorized into primes to solve the problems, right? It was obvious to us from, I don't know, from primary schools, right? That any integer can be factorized into prime numbers in only one way, right? It's so much embedded into our thinking. But it turns out that when you go to higher number fields, it doesn't happen, which caught mathematicians by surprise a little bit. But I mean, that's we being too optimistic, right? There's no reason to expect why higher number fields have to be unique factorization domains, right? It turns out it doesn't happen. This is the bad news. An example. So if you take 6 inside z root, inside this ring of integers, there are two ways it can be factorized. It's either 2 times 3 or 1 plus minus root 5 times 1 minus root 5. So there's no unique way to factorize things. There are at least two ways to factorize it. So that's one of the reasons why we cannot follow the steps I followed in the very first example for general number fields. So already we have a problem, right? So yeah, it cannot be uniquely factorized. So that means it's not a principal ideal domain, which I didn't define. But if you already know what that means, good. So this is not a PID. But if you don't know, don't worry about it. This only says that this ring of integers is bad, not well behaved, and there's no unique factorization theorem. So we want to understand how bad it is, right? We want to understand how far is a number field from being a principal ideal domain. So there's a way to measure that. There's a way to quantify that. So this is the definition of that. Again, don't worry about the definition. I just put the definition because I have to, and in case if someone is there who already knows some ring theory, can understand it. But even if you don't understand it, it's fine. I just wanted to say that there's a object which measures how far away a number field is from being a PID. Okay, so how bad it is, that's what this class group measures. So it is in fact a group, it turns out. It is an abelian group. So it measures how bad the number field is, but it itself is a group. And it turns out it's a finite group and it's abelian. And the size of this group is called the class number, which is very celebrated in number theory because it's really important. We care about that a lot. Yeah. So how do we prove that the class number is always finite? There are a couple of proofs. One of the proofs I find very interesting is you look at this ring of integers, okay, in a n-dimensional space. So I didn't say about the degree of a field extension. So for a field extension, there's what we call a degree of that. So if you have a number field k, there's a degree for that field extension k over q. So if the degree is n, you should actually visualize these ring of integers in an n-dimensional vector in n-dimensional space, and in that n-dimensional space, this ring of integers would form a lattice, like a lattice. You know what a lattice is like. It's so if you look at sodium chloride lattice, you have like dots discretely distributed right throughout the 3D space. So this is a lattice living in an n-dimensional space. Even though all of these are real numbers, the correct way to look at these things is living inside an n-dimensional space. And it turns out that this class number, we can give a bound to the class number using the core volume in that lattice. Meaning, so if you have a lattice, you can look at that lattice will make up like cubes, right? Not perfect cubes, like tilted cubes, right? So you can write down a bound for these class numbers using the volume of those n-dimensional cubes. So when I say volume, I mean the n-dimensional volume. In that way, we can prove that these class numbers are finite. It's pretty cool. I think it's called Minkowski theory, and it's really cool to see using ideas from elementary geometry to prove something very arithmetic like this. All right, let's move on. Okay, so far I'm only talking of I only talked about the algebraic side of the story, right? I defined the class group. I talked about number fields, ring of integers, all those algebraic arithmetic objects, right? Now let's do some analysis. Okay. So yeah, sort of unexpectedly, analysis comes into the picture. So if again, we have to look at a number field K. Okay. If K is a number field, we look at what we call the Dedekind zeta function of it, of K. Again, we have a formula for that. So this is the definition. It's an infinite product, and the product runs through all primes in the ring of integers. Again, I'm telling you that if you understand the notation, it's good. If you don't, please don't worry about it. I'm just saying that there's an analytic object, a complex value object out there, which is made out of the data coming from the number field. Okay. I'm just saying we have some data coming from the number field. Out of that, we make an analytic object. Okay. Analytic object. And this has a power series expansion. This is defined when the real part is bigger than 1, but we can analytically like extend it to all meromorphically, whatever that means, to the whole complex plane. There might be some problems at s equals 1, but it's not a big problem. Okay. And this is called Dedekind zeta function. All right. So don't worry about the notation. There's an analytic object which is attached to the number field. So it turns out that this function contains tremendous amount of arithmetic information about the ring of integers. Although it is an analytic object, it knows a lot of arithmetic information. So this is the celebrated class number formula, which is considered as a miracle among number theories. I will tell you why this is a miracle. There's a lot of notations, but I would invite you to ignore the notational complexities. I will describe why. Look at the right-hand side. The right-hand side has class number in that. So it measures how far away how far away the number field is from being a unique factorization domain. Okay. That's class group, which is algebraically defined. We have the regulator, which is again algebraically defined. I won't tell you how we defined it, but it's algebraically defined, algebraically and number theoretically defined. R is the rank of the units. It's fine. WK is the number of roots of unities. All of those things are algebraically defined. So the right-hand side is purely algebraic. The left-hand side is purely analytic. So miraculously, we have an equality. Like there's this weird, unexpected relationship between the algebra and analysis, which is very effective, very useful, and really unexpected. And yeah, I don't have enough vocabulary to explain this result. It's really cool. It amazed me. Yeah, and that's one way to look at it. A precious link between algebra and analysis. One way to look at it. Another way to look at it is this might not make sense much if you haven't done much algebra, but I'll say it anyway in case there's someone in the audience who want to learn. This can also be thought of local to global phenomena. In the right hand side, what you have is global properties of the number field, right? Class group, regulator, rules of units, and so on and so forth. The right hand side is global. The left hand side is made out of local things, right? Left hand side has to do with the zeta function, and it's made out of in each individual primes, right? We take one prime, look at its norm, and we multiply it together. So zeta function is made out of patching this local data, and somehow the patching is working, right? It gives some interesting, useful global information. So those are the two ways to look at it. But the first one is more easy to swallow, right? First one, analytic versus algebraic. So yeah, I'm going to revisit this class number formula. So take a snapshot in your mind, not the details, just there's a beautiful formula between algebra and analysis pertaining to the number fields. All right, let me move on a little bit. So, okay, so this is the second part of the title of the talk, Iwasawa theory, right? Let me tell you what we do in Iwasawa theory. So okay, class number formula is great. There's no doubt about that. But even with the help of this analysis, still the class numbers are extremely hard to compute because this regulator is giving a lot of noise. which stops us from knowing class numbers of most of the time. So therefore, for I mean, that's one of the reasons. Like for that reasons and among other reasons, it's very hard to compute if you look at each individual number field. So in Iwasawa theory, instead of looking at single number fields, we look at towers of number fields, like one top of each other, stacked as an infinite tower. So that this is Iwasawa's brilliant idea about looking at infinite towers of number fields uh, instead of looking at each of them individually. By the way, Iwasawa is a Japanese mathematician who started this field in 1950s. So yeah, so when you go up in this Iwasawa tower, sometimes we can understand the growth of the class groups, class numbers, and other information when you go up in the Iwasawa tower, and also we can analyze them in the top of the Iwasawa tower. And those results are beautiful on their own, but sometimes you can there's utility to doing that. Sometimes you can use those results on the top and come down, which we called Iwasawa coordinate, to prove really interesting results at finite levels too. So we can prove down to earth results using Iwasawa theory. That's how it started, to understand number fields and number fields. But as of now, there are a lot of other Iwasawa theorists, Iwasawa theories. There are Iwasawa theories for function fields, abelian varieties, which is an algebraic geometric object, modular forms, motives, and a couple of weeks ago, I got to know about Iwasawa theory of graphs. The regular graphs, dots and vertices, dots and edges, which you use in I don't know, networking. So there's a Iwasawa theory for those graphs too, which is pretty cool, I think. But yeah, Iwasawa theory is many things at the moment, but the origin is studying class groups and number fields. All right, so let's look at some of the details of Iwasawa theory. So I'm looking at what I call the cyclotomic ZP extension. Don't worry about it. So as I said, instead of looking at a single number field, we are looking at an infinite tower of number fields, and H infinity is the union of all the intermediate fields, okay, which I call the infinite level or the top of the Iwasawa tower. Okay. And all right, now let's get back to group theory, symmetries, right? So why do I call it the ZP tower? So I'm looking at this prime P, right? Why is this prime P significant? So I want the group of symmetries from nth layer while keeping the ground layer fixed, meaning the Galois group of Hn of H to be Z over P and C. What I mean by that in plain English, what I mean is the symmetries of shuffling the nth layer without breaking the field structure and while keeping the ground field fixed is same as the symmetries of a regular polygon with p to the power n sides, rotational symmetries of such a polygon. So that's what I mean. It's just rotational. Okay. So that's the condition which this should satisfy to be a ZP extension. Okay. And the top, we can also talk about the Galois group of H infinity of H. Even though it's an infinite field, still there are symmetries. We can talk about the Galois group. It is so-called this periodic, the ring of periodic integers, which is a limit of these projective limit of these groups. Don't worry about it much. Just think that it contains all the information about all those finite layers. Okay. So yeah, I mean, you might have learned in high school about limits, right? Limits of functions. There we can define limits of groups. So it itself is a group. Yeah. So if you want to learn these things more, I suggest you study abstract algebra. All right. And these Galois groups, okay, this Galois groups is shuffling around the, okay, before that, okay, these Galois groups gamma n are shuffling around the field elements, right? That shuffling is inherited by the class group itself. These Galois groups act on the class group too. So this Galois group gamma n not only shuffle the field, it also shuffle around the class group, which measures how bad your field is. And we in Iwasawa theory, we only focus on the P part of the class group, which is same as tensoring it by ZP, whatever that means. Okay. And we look at that P part in the top of the Iwasawa tower. So X is some object on the top of the Iwasawa tower, which contains information about the finite layers of class groups. So that's all you need to know. You don't have to worry about all this notational jargon, right? All you need to know is in top of the Iwasawa tower, there's an object which contains information about all the finite, all the class groups at the finite layer. And this completed group ring acts on that. And there's a good structure theory for such objects. And that structure theory can be used to analyze these class groups at the infinite level. And then we'll understand that better, and those results are beautiful. And then we can come back down, meaning we can do Iwasawa coefficient to understand the finite level class groups better. So yeah, there's a lot of utility to do things in the top of Iwasawa tower rather than doing it in the finite level. So I mean, it's a bit counterintuitive why an infinite level is any easier or simpler than finite layers, but it turns out that it's the case. So yeah, we don't have a choice, right? It's forced upon us. So it is the case, it's simpler, so we do it. All right. So okay. Now again, let me go back to a little bit of analysis. This is necessary for me to state the results I'm going to mention at the end of the talk. So yeah. All right, let me get to it. So HOF is an abelian extension of number fields. So this is an extension of number fields, one over the other. We have a Galois group. So what do I mean by an abelian extension? What I mean by that is the Galois group is abelian. That means in Galois group, A times B is B times A. The second condition you should ignore. There's no point in describing this notation. So for this data, we have what I call the G equivariant L function. So which is given by this formula. Okay. So again, a lot of notation. Don't worry about it. What I'm saying is there are some analytically defined object called theta, which we give the name G equivariant periodic G equivariant L function, which is an analytically defined function whose input is a complex number. This S is a complex number. So in earlier in the defined theta function, there's a formula, right? You put a complex number, you get back a complex number, right? Input is a complex number, output is a complex number. Domain is a complex number, codomain is complex numbers. Here, the domain is still a complex number. This S is a complex number. The output is the group ring over C. So I didn't define that, but let me tell you what it is. This is the set of polynomials, but the set of polynomials with coefficients in C, but the variables in the polynomials are group elements. Okay, that's the only difference. The variables of the polynomials, this x, y, z, in the polynomials are group elements. That's the group ring. So now this value, this theta doesn't spit out complex numbers, but simply group ring values. These values of this theta would look like, okay, 2 times G1 plus 3 times G2 plus 7 times G3 and so on and so forth, where G1, G2, G3 are elements in the group G. So it is still analytic because it takes values in the complex numbers and it has this analytically defined formula. Okay, still an analytic object, but it's a little bit complicated than the Dedekind theta function because this group G is involved. So now, as you can see, we are like combining algebra and analysis, right? G is the group of symmetries, and now we mix it with the analysis, right? We want the L function, the analytic object, to see the action of this group of symmetries. But yeah, so all you need to worry about is, so you don't have to understand the for at least for this talk, you don't need to understand the notation or the details. All the time you should think what are the information does this object carry. So what are the information does this G equivariant L function carry? Some information coming from the number fields of the prime of the number fields, analytically defined, and it spits out group ring elements, which means some element that has something to do with this group of symmetries. That's all you need to know. All right. And so a priori, this is only defined when real part of S is bigger than 1, but we can extend it in a reasonable way to the whole complex plane. All right. And okay, so a priori, the coefficients are in complex numbers, right? But we can prove that these sets S and T are nice. These coefficients in fact become integers, which is nice because we like integers, right? It's easy, they are easier to handle. So that's an observation which is not trivial but good to have. Still, these things are analytically defined objects. All right. Now I'm ready to state the theorem I wanted to state. Okay, so this is a theorem due to myself and Popescu. We proved this in 2022. This is called the equivariant main conjecture. This has a long history. This conjecture has a long history. Even though this is called a conjecture, now this is a theorem. Okay, this is proved, and I'll explain what it means to a certain extent, but I won't explain the notation. I don't think you need the notation to understand the idea behind this result. So if you look at the result, there's what we call the Selmer, right? Selmer module. So this Iwasawa Selmer module is some arithmetically significant object. That's all you need to know. It contains object. It contains information about this class number. That's what this sequence means. So the Selmer module is an object. It contains information about the class group. So it is algebraically defined. It's an algebraic object which contains information about the class group, which is what we need to know algebraically. And the left-hand side, you see the G size. The curly G is the Galois group of the infinite level over the round level. Okay, the Galois group of symmetries. We know the G size. The left-hand side is the G size of that arithmetic algebraic object. Now let's look at the right-hand side. The right-hand side is built out of these L functions, group ring valued L functions, and and it takes values in the completed group ring. But anyway, the point is the right-hand side is analytically defined, right? It's an L function. I mean, the bottom line, it's an L function, right? So what you see is an algebraically defined object. The size of an algebraically defined object is equal to an analytic object. So this is again pretty much the same as the class number formula, right? So let me go back to the class number formula. So what did we have there? We had left-hand side an analytically defined object and a zeta function. On the right-hand side, we had some algebraic object which has something to do with the class number, right? Now let's fast forward. Now theorem, the left-hand side, we have algebraically defined object, and we look at the size of that. It's just like class number, taking the class number. And it turns out that miraculously, it's equal to an analytic object. So as I said, you should think of this as a class number formula. But the difference is instead of finite levels, this is now happening at the top of an Iwasawa tower. And the classical class number formula is happening inside the complex numbers, right? But now this is happening inside the equivariant Iwasawa algebra. Some ring, I'm not going to explain, but it's living in the top of the Iwasawa tower. I should mention that. So yeah, so this is a Iwasawa class number formula, I would say. That's our result. Yeah, and there are a lot of applications in this which I'm not going to go into. But I will mention one of the applications, which is not a direct application, which is this one. So yeah, so I should briefly mention how we got here. So this is happening in the top of Iwasawa tower, right? So what we did was we used Iwasawa coordinate, came to the ground level, and used a certain transpose operation vaguely speaking, and then went up in the Iwasawa tower again, right? We came back in the Iwasawa tower, transposed, went back to the top of the Iwasawa tower again to obtain this formula. So this is also a certain class number living on the top of the Iwasawa tower. Okay. P part of the class number living in the top of the Iwasawa tower, regardless of what the notational jargon. Now we have an explicit formula for that class number, as long as the Galois equivariant behavior is concerned. So left hand side is the size of the class number, the G size of the class number, whatever that means. On the right hand side, we have things coming from analysis. Here, there's a little bit of algebra here, which I'm not going to describe the notation, but it's algebraic, but this part is analytic. So the whole thing becomes analytic. So again, algebra, analysis. So we have another class number formula here. So yeah, I think that's all I have to, that's all I prepared for today. I hope you enjoyed the talk. And yeah, I'm happy to answer any question you might have. Thank you very much for having me again. Yeah, thanks.
Yes, thank you, Mr. Rusiru, for conducting a very interesting session. Now it's the time for the audience to clarify their doubts. So I'll direct the questions we have to you now, Mr. Rusiru. Okay, so first, a certain participant had asked, in the examples for number theory shown, is there a particular reason for no odd number to exist as a perfect number when taking the sum of its factors?
Yeah, so we don't know, like we have our best people working on that now. So we actually don't know. So it's an unsolved problem. So we don't know why, we don't know, as far as I know, there's no much progress in that area. So we don't know why there's no odd number, or there's an odd number which is perfect at all. It's just, since we have these big computers, we haven't found any odd numbers. We can like check up to like very big integers, right? So we haven't found any. For that reason, we kind of believe that, it's just a belief, which we could be wrong. We believe that there's no such odd number, but it's just a experimental evidence. There's no, it's not a theoretical evidence, it's experimental. In mathematics, we want proofs, not scientific evidence. So yeah, it's unsolved, bottom line. Thanks.
Thanks, Mr. Rusiru, for that. And then another person had asked that, sir, if possible, can you briefly explain how the groups are broken into simple groups?
Oh yeah, it's a very good question. So again, I'm sorry, it's going to take a while, but I will briefly describe that. So if you have a group, there's what you call a normal group to a group. Okay. So it is a, okay. So okay, let me think of a succinct way to describe what a normal group is. So okay, let me say it in this way. So you have a group, right? And the group itself can be shuffled around. Okay, those are called automorphisms of the group. There's a special types of automorphisms called inner automorphisms. So it's again shuffling, way of shuffling things inside the group. So what happens with normal groups are, if you take a normal subgroup, inside the subgroup, if you do this inner automorphisms, inner shufflings, the normal group will be unchanged. It won't be changed as a set. So it's like you have a group in the middle, in the core there are normal groups which doesn't shuffle around as much when you use inner automorphism. So it's like the core of a, it's like a core of a group. Okay. There's not, I mean, there can be many normal groups, there can be many cores to a group, but you can like visualize very vaguely as the core of a group. And when you have a core like that, when you have a big group and a smaller normal group like that, you can divide groups. We call it coarsening out. So what do I mean by dividing? It's hard to explain, but it's a certain sense of dividing. So when you take a big number and divide it by something, you get a smaller number, right? Just like that, when you take a group and quotient it out or divide it by a normal subgroup, we get a smaller group. In that way, we can, very vaguely speaking, we can break it down to small and smaller groups. The thing with simple groups is the atoms of symmetry. Those things do not have any normal subgroups inside of them, except for the trivial group and itself. So there are no non-trivial normal subgroups living inside these simple groups. So you cannot divide it by anything. So if you take the monster is big, huge, right? 8 times 10 to the power of 53. No matter how big it is, still doesn't have a core in that, which makes it weird. But yeah, that's what I mean by like breaking it into smaller groups, modding out by cautioning out by normal subgroups. I hope I understand. I hope I answered your question. To understand what normal groups are, I think you really need to look at the details, but that's the big picture, I would say. Yeah.
Yeah. If that was clear. And then another person had asked a question about the Rubik cube, the example you gave earlier. Sir, how the number of iterations of Rubik cube is calculated, and can we do that with using those six?
So yeah, so okay, let me go back to that slide. Okay, so all right, so we have the Rubik cube, right? So we are looking at the symmetries of Rubik cube. When I say symmetries, what I mean is the ways to shuffle it around without breaking the Rubik cube. That means what you do in real life, right? You shuffle it around. So we all know that there are only 6 ways to shuffle a Rubik cube, right? There are 6 phases. In each step, we will shuffle those phases, right? So that's why I say that this group is generated by those 6 elements. But are there only 6 elements? Of course not. Why? We can first shuffle F, then B, and then do it sequentially, right? Those strings of operations will give more and more group elements, because those are different types of permutations, right? So if you look at those things, all of those permutations, there are this number of those. That's why this is the order of the Rubik cubes group. So you might wonder, okay, if you can do it in a random order, aren't there, okay, you might ask, aren't there infinitely many elements such that? Because I mean, there are infinitely many strings of letters F, B, U, D, L, R, right? You can write it in infinitely many ways, right? You can go on and on and on. Why aren't there infinitely many of them? Because after a while things will collapse. These are not free operations. There are a lot of connections in between these operations F, B, U, D, L, R. So these relations of these generators will force us these big strings to collapse down. So as I said, so you cannot have like arbitrary large strings of operations without collapsing. No matter how long you shuffle around the Rubik cube, whatever your eventual state is, that state can be achieved within 20 steps. Meaning there are enough relations in the group theory language, there are enough relations in between these generators to make sure that no matter what element you take in the group, that element can be written as a string of at most 20 generators. Yeah. I don't know whether I answered that question. Please feel free to ask follow-up questions. Okay. Yeah.
And the participant can use the chat even now to ask your questions. And another person had asked whether you can share the slides as a PDF, maybe
Yeah,
to
happy.
study further.
Of course. Sure.
Okay, then we can put it in the group. We can discuss and do that. And also another one has asked, what are the books you recommend to study these areas further?
Oh, okay. So depends on what we're talking about, the group theory or number theory. So I'll discuss both. So in order to study number theory, you of course first you have to study abstract algebra, in which group theory is a part of. So if you are starting out to study number theory, first maybe start with elementary number theory, since unfortunately in our school curriculum we are not exposed to any number theory, I would say. So maybe it won't be so bad to do some elementary number theory, um, to familiarize yourself with very basic ideas. I can recommend some books to you if you want. And then you should you should like equip yourself with this new technology. You really need to understand what algebra, you really need to understand abstract algebra. So you need to understand group theory, ring theory, field theory, module theory, homological algebra, those kind of stuff. I'm not here to scare you off, okay? These things are necessary to understand, but can be done. I'm just saying these things will help you to digest the algebraic number theory much better. These things will make algebraic number theory much more natural to you, and also it's necessary, I would say. And also then that's the algebra part. As you saw in the talk, you need a lot of analysis too, right? So you need to learn analysis. You need to learn real analysis and complex analysis. So those two are like necessary, I would say. Then if you're done with that, you can read some algebraic number theory, some analytic number theory, and see which part you might like more. I myself like the algebraic flavor in number theory, so I do that. So like people are different, right? So you might like analytic number theory. And then learning some topology, which is this study of spaces, and some algebraic geometry will come in handy, but that's later in your career. So I wouldn't worry much about that now. For the moment, learn some elementary number theory and then some algebra and analysis. That's the main thing you should be equipped with. Yeah, I can suggest some books. I could send some references.
Yeah, then we can put it in the group phone if needed.
Oh yeah,
Yeah.
let me think.
So that's all the questions received for today, Mr. Rusiru. And thank you for the audience for engaging in this session. And also, again, I especially thank you, Mr. Rusiru, for making this a very informative presentation and answering our questions.